Thanks. Can everybody hear me okay? I'm going to go ahead and share my screen. Does that look good to you, Max? Can you see it?
Yeah, I can see it. It works.
Great. So thanks everyone for coming today. I'm excited to be giving this talk. I want to give a quick shout out to Laurel Schaefer, who's up at 7 a.m. to watch the talk on the West Coast. Yeah, let's get started. So I'm going to tell you today about some work that we've been doing in my group at Colgate University, experimental and computational, trying to understand how Milstein's catalyst is active in ester hydrogenation. So first, I want to lead with some acknowledgments. At Colgate, we're an undergraduate-only university, so all of the research that I'm going to present was done by some undergraduate students in my lab. This long list here dates back to the beginning of our project on this metal-ligand cooperative catalysis. And kind of the recent people here are the ones who have worked on this project involving Milstein's catalyst in particular. We also collaborate with Jason Keith, who is my colleague at Colgate, on computational work. So Milstein's catalyst is well known. I don't need to give it very much of an introduction, but to kind of briefly explain it, this was reported first in 2005 as an active catalyst for the dehydrogenative coupling of alcohols to give esters, right here. And then in the intervening years, this complex, which is now commercially available in STREM, has been used for a wide variety of hydrogenative and dehydrogenative reactions of polar bonds, so vastly expanding on the original substrate scope of the Noyori type catalysts for ketone and imine hydrogenation and related reactions. The commercially available catalyst is this hydridochloride form here. Notice the PNN pincer ligand with a diethylamino substituent. If this is reacted with strong base, the linker position here, the CH2 linker next to phosphine, is deprotonated to make this dearomatized compound, which then reacts even at room temperature with hydrogen gas to become hydrogenated. So H plus adds to the linker and then H minus to the metal to make this hydrogenated form. Milstein's original proposed mechanism for the reaction, one key observation at the time was that a PNP version of the linker of the ligand didn't work. So this diethylamino group was key to catalysis somehow. And in the original proposal, the Milstein group proposed that dechelation was important for catalysis. So the nitrogen coming off of the metal to make room for substrate through an inner sphere type of a mechanism. Also important to the proposed mechanism, and based on those experimental observations, was this reaction of the dearomatized form of the catalyst with hydrogen to activate to form this dihydride complex. So since the original work, there has been a lot of catalytic application of this particular complex, and also a lot of computational study trying to understand how the mechanisms of these various catalytic processes work. And this list of papers here, every single one of these papers is primarily a computational, in some cases combined experimental computational work, looking at the mechanism of various reactions catalyzed by Milstein's catalyst. So there's a review from Mike Hall's group, several studies on this catalyst, which was reported in Science for oxygen evolution, dehydrogenative amide formation, hydrogenation of carbonate esters, regular esters and the dehydrogenative formation of esters, and then a couple of other related reactions. What I want to emphasize here is that in all of these studies, these two species are, or at least one of them is used as an on-cycle catalytic intermediate. And in many cases, the reaction of the dearomatized complex with hydrogen to make this dihydride, or the reverse if we're doing a dehydrogenation, are a key step in the catalytic cycle. Meanwhile, while Milstein's catalyst has found many important applications in catalysis, there's been also a lot of optimization of structures for reactions like ester hydrogenation, which was in one of these original reports for this catalyst. And I'm showing here a series of some of the most highly active catalysts for ester hydrogenation in particular, coming from various groups all over the world. And what I want to point out here is that there has been really a convergence on this NH functional group in the catalyst in many of the highly optimized catalyst structures. Most of these are ruthenium complexes, one is osmium, And there have also been manganese, for example, some first row metal catalysts that are typically somewhat less active, but still in some cases very good. But only one of these really elite catalysts for ester hydrogenation doesn't feature an NH functional group on it. And it's this one from Joe, 2014, that has a PNNP type pincer on it. This one gave 10,000 turnovers and was active at room temperature in the presence of a strong base. So again, the NH functional group is seemingly important for high catalytic activity in this reaction. Now, on the other hand, I want to present a series of catalysts that were also active for ester hydrogenation, usually not really elite high activity, but still good activity, that don't have an NH group and instead have kind of a dialkylamine group on the side chain. So for example, Milstein's original catalyst has this structure. Sanchez and Song made carbene, N-heterocyclic carbene, CNN pincer versions of a similar structure with either these pyrrolidine or diethylamino type side groups. The Joe catalyst has a diethylamine side group, and this is the one that actually is really highly active. And then in our group, we have developed some more N-heterocyclic carbene types of complexes here. A key difference between ours and the Song and Sanchez variants is the lack of a CH2 linker between the N-heterocyclic carbene and the pyridine rings. So to explain to you how we came to design this particular form of the catalyst, the original Milstein's catalyst has CH2 linkers connecting the phosphine and amine side groups to the pyridine central group in the pincer ligand. Song's ligands have a CH2 connecting the N-heterocyclic carbene ring with the pyridine ring, and this was proposed to be important in catalysis. Song showed in his work that deprotonating this linker was possible, and also showed that you could deprotonate on the other side, but it was approximately 9 kilocalories per mole higher in energy to do so. So we were interested in probing whether this CH2 linker is important for catalysis and whether catalysis might also be able to proceed through other types of reactivity. And we made a whole series of different catalyst variants here, changing the steric bulk on the N-heterocyclic carbene and the amine side. So after making kind of one of these variants, we started testing catalytic activity, and early on found that our catalyst structure in general was highly active for ester hydrogenation. And over the years, this slide is representing many years of work by a whole large group of students here pictured on the bottom, or their names are listed on the bottom, where we made 8 catalyst variants, changing the size, the steric bulk of the 2 R groups, and tested all of those catalyst variants with 3 different ester substrates at a range of catalyst loadings. And all of this data points to a key structure-activity relationship. On the N-heterocyclic carbene side, having a bulky side group gives the more active catalysts. So a diisopropyl phenyl group was the best group in terms of giving high turnover numbers in catalysis. The NR2 group also turned out to be really important. So both diethylamino and diisopropylamino side groups gave highly active catalysts. And a dimethylamino side group kind of just completely falls off. It's a huge difference to go from diethylamino to dimethylamino in our catalyst system. And this was something that really surprised us and made us think that there might be some key mechanistic information in that particular structure effect on catalytic activity. So in the course of trying to study our catalysts to see what they do under catalytic conditions, we observed a couple of interesting and surprising stoichiometric transformations of the ruthenium complexes. So our precursor form here is a hydridochloride, right? A hydrogen and chlorine bound to the metal. If we activate with strong base, in the presence of tricyclohexylphosphine, we see this kind of surprising, strange rollover reaction where the 2 nitrogens dechelate from the metal and the ruthenium activates a CH bond of the pyridine ring to give a CC chelated form. If we do this reaction with strong base and we don't add a psi3 ligand, we just kind of get a mess. So it's not that like the reaction doesn't happen, it's just that we can't get a clean product. If we then take this CC chelated form and heat it more, so this first was at room temperature, and then we heat the complex without any further additives to 105 degrees, which is our ester hydrogenation catalytic operating temperature. Then we see another reaction, which was even more surprising. So this is what we call a dehydroalkylation of the catalyst, where the ligand loses an R group from the nitrogen, and then a hydrogen is lost from somewhere, In the net, you can imagine it came from here, but I don't know that it necessarily comes from there in balance. And we release an equivalent of an alkane, a light alkane. So if we have a diethylamino group, then this product is ethane. We also had diisopropyl amino versions of the catalyst, and then we saw propane released. Now this reaction does not happen, the second reaction here, to form this imine complex does not happen for dimethylamino, but it does happen for diethyl and diisopropyl. To talk just briefly about the structure of this complex, it's reduced to a ruthenium 0 form. So this is an 18 electron, 5 coordinate ruthenium 0 complex. Since we've lost an R group, we now have an imine functional group on the right side and an aromatic pyridine ring. And the structure, the crystal structure is shown down here. It's close to trigonal bipyramidal with a tau parameter of about 0.24. So looking at the catalytic activity of these 3 different species showed that they seem to all point to having the same potential catalytic intermediate. So for example, the diethyl and diisopropyl versions, all 3 of these forms form highly active catalysts. Once you get to the point where you've added base, you no longer need to add base in the catalytic reaction for activity. And then really interestingly, the dimethylamino version is barely active in the HCl form, barely active in the CC chelated form, and then this reaction to form the ruthenium 0 imine complex doesn't happen at all. We get decomposition instead. So this was making us think that potentially this is a key in terms of understanding what's really happening in catalysis one way or another. So since Milstein's catalyst is very structurally analogous to ours, we wondered if this dehydroalkylation reaction would happen with that catalyst as well. And in fact, it does. So if we heat the commercially available dearomatized complex to 100 degrees in toluene with also adding tricyclohexylphosphine to trap the ruthenium 0 product, then we get clean formation of this imine complex here, this ruthenium 0 complex, which we call ru-PNN imine. And then ethane is released from the molecule. We also see the dehydroalkylation and the loss of ethane if we don't add psi3, but then we see kind of a more complex mixture of products. So this was a way to trap the product of dehydroalkylation. And note that this is a very fast reaction. So at 100 degrees, which is the catalytic operating temperature of many of the catalytic reactions I showed in the introduction, some of them are even hotter, we very quickly do this dehydroalkylation reaction. So this is happening in these catalytic reactions. We studied the catalytic activity of our various imine complexes, and surprisingly, or I guess luckily, the PNN, the derivative of Milstein's catalyst, turns out to be a really, really active catalyst for ester hydrogenation. So not to go through this whole slide, but I guess what I really want to say is that this is now it's the only catalyst known that gives a high turnover number at room temperature with no added base. So there are some highly active catalysts that operate at room temperature with usually substantial amounts of something like sodium or potassium tert-butoxide added. And there are other catalysts that are active without base at elevated temperatures, potentially 80 degrees Celsius or higher. But we're not aware of another example of a catalyst that gives thousands of turnovers at room temperature with no base additive. So this is a practically useful discovery. Now, we've been very interested in trying to understand our hydrogenation reactions, and in particular, we've wanted to do kinetic studies of the reactions to compare our computational work with our with what we can observe by experiment. So we've been working with this reactor here, and this is John Pham, who recently graduated from the group and is now a PhD student at Brown University, operating our reactor. And to make a long story short, the reactor allows us to sample liquid out of our catalytic reactions, but also to sample the gas headspace. And this is important because we were wondering if ethane and propane were being released in our catalytic reactions directly as the catalyst transforms to an activated form. So monitoring our ester hydrogenation reactions over time, I'm showing here our carbene versions of the catalyst. The red dots are showing conversion from the CC chelated forms that have not yet lost the equivalent of an alkane molecule. In those cases, in this case here, we see kind of a long induction period where the maximum rate of catalysis occurs about an hour into the reaction. If instead we use our ruthenium 0 imine form, we see a very slight induction period, but then rapid catalysis after 10 or 20 minutes. Meanwhile, if we monitor the headspace of the reaction with this CC chelated complex, we see ethane being released into the headspace in this early period in the reaction, and then it kind of levels off. So this dehydroalkylation to lose an ethyl group, to lose an ethane molecule from the pre-catalyst is happening in the catalytic reactions. When we use our diisopropyl substituted versions, so isopropyl imine or diisopropyl amine, we see essentially identical kinetic curves, and we see release of propane into the headspace in that reaction. So here we think we have a faster catalyst activation, but still this catalyst is losing propane on its way to becoming active. Doing the same study with the Milstein PNN type catalysts, we see a really stark difference in the rates of reaction, depending on whether we use the dearomatized complex or the ruthenium 0-imine complex. So the dearomatized complex has a long induction period where barely any catalytic activity is observed, and then the release of ethane even starts off a little slow, but what we see in this case is essentially the same thing, that the dearomatized complex is releasing ethane slowly throughout the course of the reaction, and this induction period shows that the starting form of the catalyst is not active. It has to convert into something. Meanwhile, the ruthenium 0-imine form is really highly active at 85 degrees Celsius and completes this reaction in about 20 minutes. So I'll remind you, this catalyst, when we used it in applications, we used it at room temperature. So there's a really important implication here, which is that this diethylamine amino form of the catalyst cannot be an on-cycle catalytic intermediate as it was originally proposed to be. So we did some further studies with this ruthenium 0-imine complex trying to probe what might be a catalytic intermediate in the reaction. For example, we first reacted the complex with hydrogen gas in an NMR tube. So this is a high pressure NMR tube at 10 bar. And we see a reversible reaction where psi3 is displaced and 2 equivalents of hydrogen gas are added. And we get the oxidative addition, the net oxidative addition to make a ruthenium dihydride, and then also the net hydrogenation of the imine functional group of the complex. So 2 equivalents of hydrogen are added. And this complex here is directly structurally analogous to the dihydride complex that you get from Milstein's PNN dearomatized version. The difference being that we have an NH functional group instead of a diethylamine group on the side. This complex then reacts very rapidly with alcohols to bubble off H2, even if you add just a small amount of alcohol, to give an alkoxide complex. And the crystal structure here has an extra equivalent of ethanol kind of in a hydrogen bonding geometry. So we have these characterized by NMR. We have crystal structures of both of them. And we're fairly confident that what happens in the catalytic reaction when we use the imine complex is that we have a conversion to this dihydride, which then converts to the alkoxide as the ester is hydrogenated to release alcohol product. So our resting state for most of the catalytic reaction is an alkoxide species like this. We're working and we're nearly completed now with the DFT study, which turns out to have been a kind of a Herculean effort to try to understand the catalytic mechanism with this new complex. So I don't want to talk too much about the entire thing. Again, this is kind of ongoing, but just to point out the predicted kinetics. So our resting state by calculation is the same as what we observe experimentally, which is an alkoxide complex like so. This is the turnover determining intermediate in catalysis. We have 3 separate sequences that make up the bicyclic catalytic reaction. Hydrogen is activated. So this is kind of a proton shuttle type hydrogen activation, where the highest barrier is the cleavage of H2 assisted by an ethanol molecule. We then have an ester hydrogenolysis mechanism, which this is reminiscent of Faraj Hassanan's mechanism for metathesis of the ethoxy and the hydride groups on the ruthenium center. So our key highest energy transition state here is this rollover from like a CH sigma complex to an O complex of the ruthenium, where first we kind of transfer a hydride to the carbonyl carbon, and then we remove an oxygen from that same carbon, making a ruthenium alkoxide again, which gets back to our catalyst resting state. Then we reduce the aldehyde in sort of a similar manner, but basically a stepwise transfer of hydride and proton to the carbonyl carbon, which again gets us back to our metal alkoxide eventually. So we've been doing kinetic studies of our reaction. Basically, this allows us to look at our DFT results and to see if these turnover determining intermediates and transition states actually play out in experiments that we're able to do. And this is kind of a cartoon of a potential energy surface showing the turnover determining intermediate, and then we have two similar energy turnover determining transition states. And depending on the concentrations of products and reactants, we can alter which one of these is the primary determining transition state. So under conditions, for example, of high ethyl acetate, we can see saturation in ethyl acetate to make the first step rate limiting, in which case we have this rate law, first order in ruthenium and hydrogen, and inverse first order in ethanol, or in whatever alcohol we're using. At lower ethyl acetate concentrations, now the second step becomes turnover determining, and we get a slightly more complicated rate law with ethyl acetate first order and then inverse second order in the ethanol and the alcohol complex, or the alcohol product. So we've been doing a lot of experiments, and this basic model that I showed is playing out in terms of how the data look. So a typical time course of our catalytic reaction looks like this. We see a brief induction period, which is associated with the imine complex being hydrogenated in the first place. The purple color goes away at this point right here as well, and we get a yellow complex indicative of our dihydride or our alkoxide. And then mostly what look like pseudo first order kinetics for most of the reaction. So the log plot is linear after about 30 to 45 minutes of induction period of our catalytic reaction. So this is a case where we're essentially pseudo first order in ethyl acid or in hexyl hexanoate. We're first order in ruthenium, so adding a higher concentration of ruthenium catalyst gives a larger pseudo first order rate constant. We're first order under our standard conditions in the pressure of hydrogen gas, so going from 10 bar to 40 bar also gives a linear increase in the overall observed rate constant. And then the dependence on both ester and alcohol concentrations is complicated because of the fact that we have saturation kinetics occurring in the ester and also inhibition by the alcohol under the same conditions. So we've run a wide range of reactions here, a 10-fold or I think 100-fold differences in the initial concentration of ester, and also adding alcohol at the starting point in some of these reactions. And what I'm showing you here is the result of a model in a program called COPASI that does numerical modeling of all of your kinetic data against a model and allows the rate constants to be determined. And our model essentially looks like this, where we have some catalyst resting state, which would be our alkoxide species, that can lose an alcohol to make an intermediate, lose another alcohol to make another intermediate, and eventually react with ester to complete the catalytic cycle. So this model doesn't yet have the hydrogen reaction in it, but it does account for the dependence on the ester and alcohol concentrations. So we're still working on all of this, and we hope to be completing all of this work and putting it into a publication that you'll see on ChemArchive fairly soon. To take you back to the kind of key observation that I discussed earlier, the fact that this diethylamino form of the Milstein catalyst is not active in ester hydrogenation potentially has broad implications for these other reactions I talked about at the beginning, because they're all run under sort of similar conditions, high temperatures, where the dehydroalkylation might be expected to be rapid. So we think that this type of reaction could be happening in many of these catalytic reactions, and that an NH functional group could be important in a lot of them, although we haven't had the chance to probe this experimentally yet. And I also want to point out that in the Milstein group, they have determined that an NH functional group is indeed highly beneficial for their form of the catalyst. So they have this NH-T-butyl version of the catalyst that's been shown to be really highly active for a range of reactions and more highly active than the diethylamino form. So I just want to kind of bring you back at the end to all of this DFT work that showed all of this work was using a complex like this as a key catalytic intermediate, or the dihydride form. And our experimental work shows that those complexes are not active, at least in ester hydrogenation. So I think it's worth kind of a second look at whether a lower overall barrier might be possible if an NH is included in that work. So that's all I have to say. If anyone has any questions, please let me know. I'm sorry, I know I talked a couple of extra minutes. And find me on Twitter if you'd like to discuss any of this further. Thanks everyone for listening.
Okay, thank you, Anthony, for this great talk. So one question from my side. it feels like it's just very hard or potentially impossible to really measure the kinetics accurately, because you never know. Well, I mean, for a specific complex, because you really never know what happens under these reaction conditions. Because I feel like for all the work also we've done, every time we have some sort of catalyst degradation, but it's always hard to actually notice that, because whatever you actually form is just another new active catalyst for ester dehydrogenation. Like, it seems like whatever you do destroy your catalyst, you will just create a new one. And I think this the series really shows the same. So do you think if we, for example, change to manganese or iron, which are now also being quite a few times used to do these hydrogenation reactions, we could maybe find a system where not all degradation products are active catalysts for the same reaction?
I don't know. I mean, I'll tell you one thing that I've observed in reading the papers on the manganese work is that in those cases, there's no activity observed at all for the diethylamino form of that ligand, but the NH-T-butyl form is highly active. So my hypothesis to that would say that the manganese is not capable of mediating that dehydroalkylation reaction, but still, once you get an NH form of the catalyst, you can get high activity. And I guess I want to take this chance to congratulate you on your work with the PNP ligands that makes the crazy tripod that's also active in catalysis. That was really interesting work. And it gets me excited thinking about like what might actually be in our catalytic reactions. But yeah, you really need like a super favorable case for the kinetics to be analyzable. Even ours, it's, I think we have just one active species, but still it's very complicated in terms of the effects of all of the different reactants and products on the rate.
Okay. So I think I've seen Laura Schaefer raising her hand. I'm not sure if this, but it's not anymore. I'm not sure if this is still valid. If so, please just raise your hand. Yeah, exactly. Again, but before that, I'll just ask you another question from the Q&A, which is from Daniel Tyndall, which is, thank you for these great insights. Have you had a look at how the complex looks like at the end of the reaction using Milstein's catalyst? Should give you the same complexes at the end of the reaction?
Yeah, good question. So the alkoxide is the resting state throughout the catalytic reactions that we run at room temperature with our PNN imine catalyst. If you use Milstein's precursor, I think that it's just, you have to run it at such a high temperature to activate the catalyst that it decomposes rapidly, and it's never one clean species. So I think that there's kind of this weird issue where the catalyst is really active. Its overall turnover frequency barrier is only 18 kcal per mole, but the barrier to activate it is like 26. So like if you try to see what's happening in like with the resting state of the original Milstein catalyst, you get a mess at all time points. There's a little bit of whatever's active and most of it's decomposing.
Okay, we have one more question before you quickly need to run to your teaching, which is, can you please briefly share your thoughts about the role of the tricyclohexane phosphine? Is the ruthenium imine formation specific to that?
Yeah, so if you do the same dehydroalkylation without adding any tricyclohexylphosphine, then you see ethane in the headspace in the NMR tube. So the reaction still happens, but you get a mess of ruthenium complexes. So I think the ruthenium zero it's basically trapping that, the tricyclohexylphosphine is trapping that ruthenium zero intermediate to make it a clean reaction. And then in catalysis, I think the psi3 just gets out of the way. It goes away and allows the reaction with hydrogen to make this dihydride form, which is active. So we've done experiments, I didn't show these, where we add various amounts of psi3 and we see inhibition of catalysis, right? What it does is it pushes the equilibrium toward the psi3 ruthenium zero imine, which is an inactive form, and away from the dihydride form, which needs to dissociate the psi3. So, I mean, it does give us a really stable, isolable crystalline form of pre-catalyst, but it creates its own induction period.
Okay, so then thank you. I don't see any more questions at the moment in the chat or Q&A. So yeah, thank you again for the great presentation, and we'll